What would happen if you continually cut an apple in half, again and again and again and again? The Greek philosopher Democritus reasoned that eventually you reach a point where the apple, or more generally matter, could not be cut any further. He termed this final uncuttable matter Atomos, Greek for uncuttable. However simple this idea is, it set the course for a scientific epic that helps us in understanding the vastness of a universe through the pursuit of finding its smallest units. Unfortunately, a far more famous and for the time influential philosopher, Aristotle, would laugh at the idea of Democritus's uncuttable Atomos. For 2,000 years, no one would think of atoms again. It really makes you think what else has not been yet appreciated for its worth, lost in history, potentially forever. Thankfully, John Dalton, a schoolteacher and part-time researcher, revived the idea of the atom. Dalton's work described the first atomic theory. Okay, I'm not going to get too bogged down with Dalton's atomic theory because it does get outdated rather quickly. Over time, scientific theories often evolve, and Dalton's atomic theory is no exception. When we look at Dalton's billiard ball model of the atom, it shows the atom as the most fundamental unit of matter. That means it cannot be broken down into any further units. Now, this idea of the atom being the fundamental unit of matter was disputed when J.J. Thomson founded a negatively charged particle, which he called a corpuscle. Thankfully, the name didn't stick, and we know them today as electrons. Now, since electrons were shown to be negatively charged, and atoms were self-contained units, it was hypothesized that the electrons lived within the atom surrounded by positively charged clouds. Now, the next revision of the atomic model comes from Ernest Rutherford, who shot special particles called alpha particles towards atoms and measured the angle of deflections. Most of the alpha particles shot at the atom would run straight through the atom. However, some would deflect off at drastic angles. Therefore, Rutherford modeled the atom with electrons orbiting around a compact, positively charged center called the nucleus. This nucleus was assigned a positive charge. Niels Bohr would refine this model by modeling the electrons orbiting at fixed orbits and energies, much like planets orbiting our sun. Bohr is also celebrated for discovering the particle responsible for the positively charged nucleus, known today as the proton. Now, shortly after, another particle that exists alongside protons within the nucleus was discovered, known today as neutrons. These neutrons are neutrally charged. So with this in mind, we have a picture of an atom that's made of electrons, protons, and neutrons. Now, although Niels Bohr's planetary model is probably the most convenient and intuitive in visualizing the protons, neutrons, and electrons of the atom, Erwin Schrödinger would flip the world on its head, producing one of the most widely accepted, accurate, and unfortunately unintuitive model of the atom. This model is known as the quantum model. And in quantum mechanics, the electron is not only a particle, but also a wave. Don't worry if you don't understand this. One of my favorite quotes regarding quantum mechanics goes something like, "If you think that you understand quantum mechanics, then you don't." It is an incredibly unintuitive model, however experimental data agrees with its predictions. What's interesting is the fact that the electron exists as a particle and a wave sets definitive limits on our accuracy and precision in observation. Now, although at face value this may seem innocuous, it has serious implications philosophically. For many students, they're going to focus on the Niels Bohr planetary model of the atom. It explains a lot of chemical properties, and it's far more intuitive, allowing you to learn at a faster rate compared to jumping straight into the confusion that is quantum mechanics. Now, lastly, for those of you that are wondering if protons, neutrons, and electrons are truly the fundamental units of the atom, you might want to look into particle physics, specifically the Standard Model. Physicists have been smashing atoms together and studying the resulting particles and energies of the very momentarily broken atoms. What we currently believe are truly the fundamental units of our universe have been organized into what's called the Standard Model of particle physics. Electrons look to be truly fundamental. Protons and neutrons, however, are made up of special particles called quarks. Now, the Standard Model involves many different fundamental particles. It involves mysterious particles like quarks, leptons, and the most recently discovered Higgs boson. These findings sit at the very edge of our current understanding.